Dear friends, today we are seeing about sums and areas. In the last section, we saw the formula for distance in terms of velocity, that is delta d is equal to sigma I is equal to 1 to n V I into delta T I. That is, when the velocity is a constant V I and the time interval T I is delta T I is considered, that is during the time interval T I minus 1 T I. In this section, let us study the geometric interpretation of this fact, which is important in the study of integration. Let us plot the velocity of a bus as a function of time. Suppose that the total time interval is closed interval a b, that is from the position A to B, and this interval is divided into smaller intervals. A is equal to T naught less than T1 less than T2 etc. less than Tn is equal to B. The ith interval is open interval Ti minus 1 Ti, and the velocity is constant Vi on this interval. The graph of V, it is as shown in this figure. Here in this figure 5.1, n is equal to 5, that is we are considering 5 time intervals and 5 velocities T naught, T1, T2, T3, T4 and T5 are the time bounds, and the velocities are V1, V2, V3, V4 and V5. In the first interval, the velocity is delta V1 and the time is delta T1, that is T1 minus T naught. In the second interval T1, T2, delta Ti will become T2 minus T1 and the velocity is V2. Then in the third interval T3 to T2 you will get delta T3, it is equal to actually T3 minus T2 and the velocity is becoming V3. Next the velocity is decreasing, it is becoming V4 in the time interval delta T4, that is T4 minus T3. In the next time interval T4 T5 delta T5 it is equal to T5 minus T4 and the velocity is becoming V5. So, when we are considering this figure, it is possible to identify the velocities and the times given, the total displacement. Delta d will become sigma V I delta T I. So, we can find the sum of all the areas of the given rectangle and we can find the total distance which is covered by the bus. The area under the graph of a function. So, let us consider a function f be a real valued non-negative function defined on closed interval a b. Then the area under the graph of the function, how will you find? On the interval closed interval a b. It is defined to be the area of the region in the plane enclosed by the graph y is equal to f of x, the x axis and the vertical lines x equal to a and x equal to b. Now, let us examine the real plane, the real function between these planes and also the properties of the sums and areas. To find the property sigma I is equal to m to p or sigma I is equal to m to n a I plus sigma I is equal to n plus 1 to p a I of the sums. Previously we have studied that property. So, we can expand I is equal to m to p like that. Then what is the method to find the sum is, there are corresponding respectively the addition property of the areas, that is the plane region A is split up into 2 points or 2 sets A1 and A2 as you see in the figure, which overlap only along their edges. Then the area of the region is the sum of the areas of the pores as given in the figure. So, here if you can say in the figure you can see that there are two areas. If they are overlapping, you can see that the sum could be found out in such a manner that A plus B, if you are having two different areas for capital A, you can add up those areas, and if one is a subset of the other one, you can say like that also. That is dealt in the next one, that is the inclusion property. The another property of the sum is that AI is less than or equal to BI for I is equal to m plus 1 etc. up to n. Then sigma I is equal to m to n or AI is less than or equal to sigma I is equal to m to n BI. Because AI is always less than or equal to BI, the summation of all the AIs will be less than or equal to summation of all BIs. That is, the sum counterpart for the area is the inclusion property. The property's name is inclusion property. It is one plane. If one plane is contained in another plane, the containing region has more larger area that is seen in the given figure. Then the connection between the areas and sums become more explicit if you consider a step function. A function g on the closed interval AB is called a step function if the closed interval AB is broken into smaller intervals which is contained, that is closed subintervals, which has a constant value on each part or each step. More precisely, there should be numbers x0, x1, x2, etc., xn with A equals x0 less than x1 less than x2, etc., less than xn minus 1 less than xn equals b, such that the value of the function g is a constant in each of the interval. First interval will be x0, x1, the next interval x1, x2, next one x2, x3, etc., the last one xn minus 1, xn. The precise definition of a step function and the area under it is given as below. What is the definition of a step function? A function g on the closed interval AB you are taking, it is called a step function when the closed interval AB is possible to be divided or broken into small intervals of width delta xi, on each of which the function's value g it is equal to a constant k. That is, whatever value of g you are taking, g of x is a constant ki. If each ki is positive or 0, then what happens? The area under the graph of g is sigma I is equal to 1 to n ki delta xi. That is, when you are multiplying the steps function's value ki with the width of the interval, that will constitute the area under the graph of g. So, this is the definition of step function, and it is possible to find the area of the graph under g in the closed interval AB using this summation formula. That is, you are dividing the interval AB into small parts and you are adding each of those rectangles together, you get the final area of the graph. So, here we are doing a problem number 6, that is how we will draw a graph of a step function. The question tells, draw a graph of step function defined on the interval closed interval 1, 4 by the graph g of x. The values are given in 4 steps, that is the values are 1, 3, 2, 4. First value 1 in between the interval 0 less than or equal to x less than 0.5. Next one, the value g becomes 3 if 0.5 less than x less than 2. The next value 2 if 2 less than x less than or equal to 3. The last one, the value is 4. The fourth step, 3 less than x less than or equal to 4. So, how will you find the area of the region under the graph is also asked. So, in order to find the solution, the graph of g you are trying to draw and you are trying to find the values from 0 to 4. If you are drawing the line, you can draw it like this, that is 0.5 to 1, then 1 to 2, 2 to 3 and 3 to 4. the 4 different values and the graphs are drawn, and you can just shade those part in order to find the area. What you are going to do is you will add each rectangles in the next slide. You can see that is the area under the above step function G. It is a sum of the areas of the shaded categories of the rectangles in the figure. The figure is enlarged in the previous slide and you can see it. So, the area could be now written as 1 into the difference in time interval 0.5 minus 0 plus the next value of G3 into 2 minus 0.5 the next interval, subinterval, then plus the next value of G is 2 into the next subinterval is 2, 3, so 3 minus 2. The last subinterval, the value of G is 4, the value of step function, and you will get 4 into 4 minus 3. So, when you total the value, you will get 0.5 plus 4.5 plus 2 plus 4, final value is 11. So, it is possible to find the area of a step function. You are just climbing the step one after the other and you are just counting all the path which you traveled and you will get the final area. That is all. Thank you, friends.